Okay, here I'm going to explain what we're going to do in the second activity in this lab. So our purpose is to find the moment of inertia of this mass. Now this mass is rotating about this point. You can see the mass is attached to this rotating platform. When the platform is rotating, the mass is rotating about this point or about this axis, like this. Now this is moving in a circle. You can see the radius of that circle is the distance from this point, that is the center of the axis, center of the axis to the center of this mass. We're going to consider this mass as a point mass. So this point mass is rotating in a circle. The radius of this circle is 20 centimeters. You can see this is centered at this 20 centimeter position. So then we can calculate the theoretical value of the moment of inertia using I, moment of inertia, equals mr squared. M is the mass of this mass, r is the radius. So mr squared gives the theoretical value of the moment of inertia. Find the experimental value of moment of inertia of this object. We're going to apply torque on the this system. So in this system I have the base, the platform and the square mass. Now I can connect this platform with the square mass to the base, like this. I can connect them, and you can see this axis is free to rotate. So if I apply torque on this axis, torque on this system, system will rotate. This plus the rotating platform, everything will rotate because of the torque. Now how do I apply torque? Now you can see the string is wounded around this pulley. So here I'm going to use the pulley with the highest or the biggest diameter. If I apply a force by pulling this outward, pulling the string outward, you can see this system is rotating about this axis because of the torque. Now how do I calculate the torque? Torque equals force, which is the tension is the force, tension times the perpendicular distance from the force to the pivot point or the axis of rotation. So this is the axis of rotation and this is the force, and you can see the force is always tangent to this circumference of this pulley. It's always like this. So if I can find the radius of that pulley, that is the perpendicular distance to the force from the pivot point or from the axis. So I can easily get that. I have to measure the diameter, the inner diameter. You can see this inner diameter of the that pulley, and divide that by 2. That will give the radius. Okay, the next thing is to find the tension. I know to find the tension, we have to consider the forces acting on this hanging mass. Weight acting downward and tension acting upward. So those are the two forces, and both forces are vertical. When these two forces are not equal, this hanging mass, this object will accelerate downward. The acceleration equals net force, which is weight minus tension, divided by the mass of that hanging mass. The mass of the hanging mass is 300 grams or 0.3 kilograms. So in that way we can find the tension. To find the tension, we need the acceleration of the system. To find the acceleration, we're going to use the Pasco Capstan. Now I'm going to record the data of the activity 2. Now first I'm going to get the angular acceleration and linear acceleration of the system. To get that, I'm going to record the linear speed and angular speed as a function of time when the system is accelerating, when the hanging mass accelerates downward linearly, and this platform and is accelerating rotationally about this axis. Okay, let's record data. I'm going to let this go. I'm holding this, let this go. Now the system is accelerating downward. I need few data points, so just stop recording data. And now I want to get the slope of the graphs. I have two graphs, linear speed as a function of time and angular speed as a function of time. Okay, I'm going to select only this portion of the data to calculate the acceleration. This is the time interval where the system accelerated. So select that region, and okay, so this is the slope of the graph 1.81, that is the angular acceleration. Now in order to get the linear acceleration, again I'm going to select as the linear portion of the data set and get the linear fit. Now I have the acceleration of the linear acceleration. So record this. I'm ready to record the data without the point mass. Let's record the data. So I'm going to hit record here, and I'm going to let this go from the rest. So it's moving now. I need only few data points, so stop recording. Now I can find the angular and linear accelerations. So again I'm going to select a certain portion of the graph, only the linear portion of the graph, to get the accelerations. So I select that region, and here I'm going to select only this linear region and the slope linear. Okay, I have the slope of that graph, and I'm going to get the slope of this graph as well. Okay, so the slope of that graph is slope of the linear speed graph is the linear acceleration, and here is the angular acceleration. So that's all you need to calculate the moment of inertia of the point mass.